I have a question about a concept you explained at the end of the lecture on last Friday.
End of last Friday,
Yeah,
okay.
So where you were basically trying to derive the derivatives, numerical approximation for the derivatives of a slanted grid.
Oh yes, slanted. Okay, sure.
So I understood how you did it for to derive derivatives of the first order with
Yes.
the first order approximation.
Yes.
But I can figure out a way to get a second derivative with a second order approximation or the mixed derivative, because I seems to be a very difficult way to isolate those two terms, the second derivative along the slanted axis and also the mixed derivative term, because it seems to never cancel out because they're basically the same.
Okay, so if you want to derive a scheme for a particular derivative and things that you want to cancel out never cancels out, that means you need more points.
But even if I put more points, because in the second derivative, so in the slanted curve, the derivatives along the x-axis are never going to have those components on the slanted axis because they just have x terms. Say.
Yes.
And in the slanted axis, the mixed derivative and the second derivative are always going to be proportional in terms of coefficients. So at least that's what I found. And so if you put one equation equal to 0 and the other one equal to 1, you're never going to find a solution apart from 0, 0, 0.
You're saying the second order derivative and the mixed derivative is always proportional?
Yeah, because if you say
if you take points only along the slanted direction, then it's yes. But if you also include grid points that are, for example, I-1 and J-1, then they are not going to be proportional.
I-1, the problem is that they don't have y terms because they only move along the x-axis. So you're not going to have anything to deal with the y direction. And even if you take J-1, it's the same problem. It's going to be a different sign, but the second derivative and the mixed derivative.
Yeah, what I mean is you don't just take I and J-1, I and J plus 1. You take I-1, J-1. So go to the corner. What I mean is you are having a grid like this. You want to approximate some derivative here, right? You are suggesting, okay, if I include these 4 points, maybe not enough. I may have to include this point or this point or this point or this point. If you find just the surrounding 4 points are not enough. Does that make sense?
Yeah. I haven't done the 6 points, but I'm not sure that.
Yeah, try it. Okay.
It's just that the point over there in the angle would be minus.
Yeah, try that. If you haven't tried that, try it.
I'll try.
Okay. All right. Any other common questions? Yes.
When you say the oblique mesh allows the problem to align with the features of the governing equation, I don't really
Not the features of the governing equation, the feature of the solution.
the features of the solution. What do you mean by features of this?
If you solve this, you kind of see what features I mean. Okay. Yes, just work on problem question 2 and solve it first.
Okay.
Right.
So we should take the theta as a fixed angle in the following. But you know that from the first question, the theta angle depends on the fx function, right? The boundary condition.
So it doesn't depend on the boundary condition, right? So if you solve, you can try a few different boundary conditions yourself, right?
Yeah.
And what you can observe is that the angle of the features doesn't really depend on what f of x you plug in. Okay. Any other questions? Yes.
For the angle, do we just derive that? Do we have to derive that, or just like
you can either derive that or you can observe that. You don't have to have a rigorous derivation.